Hi Trigoners! So today our topic is inverses of functions, and it's actually something that you guys have done for a while now. Before we even get into some of our problems, I'm going to talk about what inverses are at like a very basic level. So we could say that one function is like the adding 3 function, and another function would be the subtracting 3 function, and I think those represent inverses of each other, where one function is adding something and the other one is taking the exact amount away. We could also say something like multiplication, and then another one would be division. So you've been doing inverse operations for a very long time. Let's go back and use this example, and let's say what happens if you plug in 5. F of 5 is equal to 5 plus 3, which is 8. And I want to be able to plug in 8 into this function to get right back to where I started. And that's really the focus of the day, is that how can we generate a function if we don't know it already? How can we come up with g based on what f is so that it undoes all the actions of f? So one of the most important steps is what you see right here in blue, and that is the composition of any inverse should get you right back to where you started. So the composition of any pair of inverses should get you right back to where you started. What you plug in is what you get out, and it's because this function here and this function here are undoing the operations of each other. The other thing you could think about is that inputting 5, g does something to it, and f brings it right back. F undoes all those actions, and so it's like nothing happened at all. You still had this input, and it's like it never had anything done to it. So we're going to go through several situations here where we're talking about inverses, and the first question we would ask you is, are these two functions here inverses of each other? And you want to, I'm going to put a qualifier on this and say x has to be greater than or equal to 0. I think you'll understand in just a second. So what you want to check is the composition. So I'm going to start out by plugging g into f. And you get the square root of x squared, which is just equal to x, but only if you have positive numbers. If it was negative, then that wouldn't be true. So that's why it's important to have the positives. So far, this is good because what I plug in is exactly what I get out. So far, so good. We also want to check the other direction. So f goes into g. Is x minus 2 plus 2 is also equal to x. So once again, what we plug in is what we get out. And we can say, yes, f and g are inverses of each other. All right, part B. So let's check this again. We have two different functions. And again, the question is, are they inverses of each other? So I'm going to plug p into m. Find a common denominator. When you divide by 5 and then you divide by 4, it's exactly the same thing as dividing by 20 because you're dividing by both of those numbers. The other way to think about it is to say that division by 4 is the same as multiplying by the reciprocal. So that's the same as multiplying by 1/4, and either way you get to a denominator of 20. So we have x minus 21 over 20, and I do not think that is equal to x. So no, m and p are not inverses of each other. So you're looking for x. The composition has to be x if you have two functions that are inverses. Okay, so next we're getting into how we can figure out what the inverses are algebraically. Instead of doing a composition, we've got to be able to start with one and come up with the inverse through some algebra. And the idea behind it goes right back up here. What I want you to notice is that this output is also the same thing as the input into that inverse function. And if we could force that to happen for every single pair of numbers that we have, then that would achieve the inverse. And so that's going to be our first step. Make this x value exactly the same thing as that y value. And this x value is equal to that y value. And so that's just switching the two numbers right around. So j of x is the same thing as y, right? These are both just outputs and different ways of saying the output. So step number 1 is going to be to switch their places. And then step number 2 is going to be to solve for y. So you have x plus 3 is equal to 5y. Therefore, y is equal to x plus 3 over 5. And I think you should take a second and rewrite it so that it's in the inverse notation. So it's j inverse of x is equal to x plus 3 over 5. Notice here when I say it, so I'll say it again. It's j inverse of x. We don't say j to the negative 1. We say j inverse of x is equal to x over 3. Sorry, x plus 3 divided by 5. Let's do another one. So step number 1 is to switch the x and y. And step number 2 is to solve for that y value. So you have x minus 7 is equal to 4y. So y is equal to x minus 7 over 4. Therefore, C inverse of x is equal to x minus 7 over 4. There's that fancy inverse notation once again. All right, so pause the video, and I'd like for you to try C and D and E and F, and then go back to Canvas and you can check your answers. All right, so now we're going to start to pull all of this together, and we're going to see how inverses can be seen on a graph right next to the algebra and really make sure we understand domain and range. So it says we have a function f is equal to root x plus 4 minus 3. I'm actually going to wait to do the inverse algebraically once I have everything over here completed. So I'm going to start by graphing the function, and this is a square root function that has been shifted. And all of the points have been shifted to the left 4 and down 3. And I'm going to erase my parent function because I don't need to see it. Okay, so just above we found the inverses algebraically by switching the x and y value. And it's even easier on a graph because you really do just switch the x and the y points. So looking at this point, this is the point negative 4, negative 3. When you switch those around, you get negative 3, negative 4. The next point is negative 3, negative 2. It switches, you go negative 2, negative 3. 0, negative 1 goes to negative 1, 0. 5, 0 goes to the point 0, 5. So something really cool here happens when you graph inverses, and it looks like there's a mirror image, and the mirror line is the line y equals x, and that's to say if you fold the green one over the red line, it would be right on top of the purple, or you could go the other way around. If you take the purple, flip it over the red, you'd end up at the green. Looking at the domain of f, so domain, here's f. The domain of f is from negative 4 to infinity, and the range is from negative 3 to infinity. And if you look at the green function, the domain of the green function is from negative 3 to infinity, and the range goes from negative 4 all the way to infinity. And so there's that idea again, that the x's and the y's switch. So the domain of f is exactly the same thing as the range of the inverse. And the range of f is exactly the same thing as the domain of the inverse. So this is just the collection of all x points. Sorry, this one is the collection of all y points. And it had to flip-flop places with these inputs right here. So that's why all of that is starting to make sense and come together. All right, the next step is to find the inverse algebraically. So we'll start by switching those x and y points. And now we solve for y. So we add 3. square both sides, and then subtract 4. So y equals x plus 3 squared minus 4. And you don't have to call it y anymore. You know specifically that this is f inverse. However, if I were to look at this function right here, like in isolation, I would think that that's a full parabola. And when I look over here at my graph, it's just not. It's only half, right? These are only, it's half of a parabola, and it's because of how f began. F began as a square root function, so the inverse is only half of a parabola, which means I need to qualify my domain. You need to make sure that you say for what x values it's good for. Otherwise, I think you think that it's an entire parabola, which it's not. All right, number 4, let's do another one. So this time the function is x squared minus 6. It's a shift down 6 units. And this says x's are only bigger than or equal to 0, so I am going to graph it only on the right half. And right now I'm using the pattern over 1, up 1, over 1, up 3, over 1, up 5. Switch the points around, so 0, negative 6 goes to negative 6, 0. 1, negative 5 goes to negative 5, 1. 2, negative 2 goes to negative 2, 2. 3, 3 goes to 3, 3. There's that symmetry line again. The domain of f is 0 to infinity. The range of f is negative 6 to infinity. The domain of f inverse is negative 6 to infinity. And the range is 0 to infinity. Once again, there's that connection between those. All right, so our next step is to solve for the inverse algebraically. So switch x and y, solve for y. And this time, you have to take square roots. And remember that anytime you take a square root, you need to remember the plus or minus. So we have plus or minus the square root of x plus 6. Now, looking at the plus or minus, it would mean that the negative would be down here. And the thing is, we don't see that part. We only see the top branch. So when you're considering how to write your inverse function, for this example, you cross off the negative. There are examples, here today where you'll have to include the negative and cross out the positive. And so I think looking back at the graph will help you determine that. So I think f inverse is equal to the positive square root of x plus 6. All right, these next couple I'm going to get you just started on, and then you can turn off the video and try on your own and look back at the answer key. So when a function is written like this, x squared plus 6x, that's kind of in standard form. Even though we don't have a c value, I would still say that this is in standard form. And I think it's so much easier to graph and understand how to find the inverse algebraically if you're working in vertex form. So I'm going to complete the square on this function. So f is going to be equal to x squared plus 6x plus 9 minus 9 is x plus 3 squared minus 9. And that's as much as I'm going to do on that example. Just remember that you're dealing with that half of the parabola. And then number 6. This time you have a function equal to 3 minus x quantity squared, and that's a little weird for us to see. We're not really used to seeing the number come before the variable. And so just to help us understand what this is doing, I want you to think about what happens when you subtract two numbers. Any two numbers that you subtract and you switch them around, they're always opposites of each other. What happens when you square a negative? It turns positive. So really, even though this looks messy, you could rewrite this as x minus 3 squared, and it wouldn't be different. And it's because this is just opposite of whatever's inside, and the square of that negative is going to turn positive anyway. So I think that this is the easier one to consider, especially like when you graph it. All right, so go ahead and work on that one as practice, and also number 7 as practice. Have a good day.